This presentation introduces the X-EROS platform demonstration. The Extensible Reliable Offloading Solution is a hardware-based accelerator template designed for mixed critical applications. It is capable of integrating different RISC-V processors, accelerators, and coprocessors. It can operate in different execution modes. These modes include single, where only one core is active, as well as fault-tolerant configurations such as triple-core lockstep, dual-core lockstep, and staggered mode. The EROS system has been integrated into X-Heap, resulting in the X-EROS system, which has been taped out in TSMC 65nm low-power technology. The setup consists of two evaluation boards. The first hosts the X-EROS tape-out, while the second, a pink Z1, connects the X-EROS GPIOs to buttons and LEDs. A monitoring platform on the FPGA enables power measurement through the SPI-ADC. The demo runs AES-256CBC on EROS, injects a fault to observe the response in different modes, and measures power consumption for each mode, allowing a direct comparison of system behavior and energy impact. This demo begins with the initial setup of the X-EROS development board. The power supplies and clock are configured. Once initialized, OpenOCD enumerates the cores via GTAG. Then, the programs for both the X-Heap host and the EROS Safety Island are loaded. The terminal shows the main system settings, the options menu, and the results. The buttons allow changing the execution mode, injecting an error, auto-reload, and execution. The results show whether an error was detected, whether the output matches the golden copy, and the execution cycles. With auto-reload enabled, the EROS system switches between operating modes. Single, TCLS, and DCLS share the same cycle count, while staggered mode takes longer due to buffered I/O. Then, an error is injected during software execution on the EROS system. In single mode, the system is not able to detect the error, and the output does not match the golden copy. In the other fault-tolerant modes, errors are detected and the outputs remain correct. Execution time also increases due to error detection and recovery. TCLS recovery is faster thanks to its voting-based mechanism, while DCLS and staggered modes rely on slower checkpoint-based recovery. The final part measures power consumption in each mode using the monitor on the pink Z1. The first plot shows core and I/O power in single mode where one AES execution is marked. The second power measurement corresponds to TCLS mode, where one execution cycle is highlighted in the plot. This mode shows the highest power consumption since 3 cores are active in the EROS system. The next power measurement corresponds to DCLS mode. In this case, power consumption is lower than in TCLS mode, since only 2 cores are active. The last measurement corresponds to the fourth operating mode, DCLS, with staggering. In this case, a reduction in power consumption can also be observed compared to the other redundant modes.